What if everything you think you know about the beginning of the universe is just the tip of an iceberg, one that stretches into realms so strange, so counterintuitive, they defy our most basic understanding of reality? Picture this: a moment before time itself existed, before stars, before galaxies, before even the fabric of space had fully formed. What could possibly have sparked existence into being? The answer might lie in the bizarre and beautiful world of quantum physics, where particles blink in and out of existence, where the act of observation changes reality itself, and where the very foundations of our cosmos could be woven from probabilities rather than solid truths. This isn't science fiction, it's the cutting edge of our quest to understand where everything comes from. For centuries, humans have looked to the stars and wondered how it all began. Ancient myths spoke of gods and chaos, while modern science points to the Big Bang. But what if that explosive beginning was just one piece of a much deeper puzzle? Quantum origins theories suggest that the universe didn't just appear, it might have emerged from a fluctuation in a sea of infinite potential, a flicker in the quantum void that somehow became everything we see. Imagine a universe where multiple realities branch off at every moment, where time isn't linear, and where the rules we take for granted are just local bylaws in a much weirder cosmic neighborhood. These ideas don't just challenge our assumptions, they shatter them, opening doors to possibilities that feel more like dreams than equations. That's the journey we're about to take together, a deep dive into 30 of the most astonishing theories about how the universe might have begun, from the mind-bending to the downright magical. We'll explore how quantum mechanics could rewrite the story of creation, why some scientists think our universe is just one bubble in an endless froth of multiverses, and how the act of observation might have played a role in birthing reality itself. By the end, you won't just see the cosmos differently, you'll question the very nature of existence. So buckle up. The answers won't be simple, but the ride will be unforgettable. The first theory on our journey takes us to the heart of quantum strangeness, the idea that the Big Bang itself was nothing more than a random flicker in an endless, timeless void. Think about how particles pop in and out of existence in empty space, a phenomenon we've observed in labs. Now stretch that concept to cosmic scales. What if our entire universe began as one of those fleeting quantum fluctuations? A burst of energy so immense it defied the odds and didn't just vanish back into nothingness. Some physicists argue that in a sea of infinite possibility, even something as vast as our cosmos could emerge from sheer randomness, like a wave rising unexpectedly from a calm ocean. But here's where it gets mind-bending. If the Big Bang was a quantum event, the rules we rely on, cause and effect, time's arrow, might not apply. There's no before in this scenario, no clock ticking outside the universe to mark its birth. Time as we know it began with that explosion. Asking what came before is like asking what's north of the North Pole. The question might not even make sense. And yet, this theory forces us to confront an even deeper mystery. If there was no space, no time, no laws of physics before the Big Bang, what triggered that fluctuation? Was it Chinese letter chance, or could there be some hidden mechanism we haven't discovered yet? Critics point out the gaps. Quantum fluctuations we observe today happen within an existing universe governed by its rules. Applying them to the origin of everything is like using a recipe for baking a cake to explain how the oven was invented. Still, the elegance of this idea is undeniable. It strips away the need for a creator or an external force, suggesting that existence might simply be a rare but inevitable twist in the fabric of reality. Maybe universes blink into being all the time, most collapsing instantly, ours just got lucky. What if this wasn't the first universe, nor the last? Some models suggest an eternal cycle of quantum births and deaths, a multiverse where reality is endlessly rewriting itself. The implications are staggering. It means our cosmos isn't special, just one note in an infinite symphony of possibilities. And if that's true, the real question isn't how our universe began, but why this one, with its stars, planets, and us, turned out the way it did. Now, let's step into a reality where our universe isn't alone, but merely one page in an infinite cosmic library. This is the Multiverse Hypothesis, a theory so vast it redefines the word everything. At its core lies a simple but staggering idea. What we call the universe might just be one bubble in an endless froth of realities, each with its own laws, constants, and perhaps even versions of the beauty of this theory. It solves one of physics' greatest mysteries, fine-tuning. Think about gravity, the speed of light, or the charge of an electron. Tiny changes to these numbers would make stars, planets, and life impossible. So why do they fit so perfectly? The multiverse answer is shockingly elegant. If infinite universes exist with random laws, some will inevitably hit the cosmic jackpot. We're not in a tailor-made universe, we're just the lucky ones who ended up in a habitable one. It's like walking into a room with a million locked doors and finding yours already open, not because someone unlocked it for you, but because you tried every handle. But not all multiverses are created equal. Some theories suggest bubble universes where new cosmos constantly inflate like soap bubbles in a foam, each with its own physics. Others propose brain worlds where our universe floats on a higher dimensional membrane, occasionally colliding with others. Imagine cosmic bread slices bumping in a multidimensional toaster. Then there's the quantum multiverse, where every decision spins off new realities, branching endlessly like a tree growing faster than light. Here's the twist: these aren't just wild guesses. Bubble universes emerge from inflation theories, math, while brain worlds tie into string theories, hidden dimensions. Even quantum branching finds support in the famous double-slit experiment, where particles seem to explore multiple paths at once. The multiverse isn't science's Hail Mary, it's a natural extension of our best physics. Yet critics demand proof. If other universes are forever cut off from us, how can we test their existence? Some hunt for bruises in the cosmic microwave background, scars from ancient brain collisions, or anomalies in quantum probabilities. Others argue the multiverse isn't science at all, just untestable philosophy dressed in equations. But consider this: 2 centuries ago, the idea of galaxies beyond our Milky Way seemed absurd. Today, we know the observable universe holds 2 trillion of them. Could the multiverse be tomorrow's settled fact? Whether it's right or wrong, the theory forces us to confront a humbling truth. Reality might be far bigger, stranger, and more generous with second chances than we ever dreamed. After all, in an infinite multiverse, every impossible thing happens somewhere, including this conversation. Now let's shatter another cosmic assumption, the idea that our universe began with a bang and will end with a whimper. Loop quantum gravity, one of the most promising theories attempting to unite quantum mechanics and general relativity, offers a radically different vision, a universe that breathes. Imagine the cosmos not as a one-time explosion, but as an eternal heartbeat, expanding and contracting in an endless cycle of rebirth. This theory doesn't just tweak the Big Bang, it erases the singularity entirely, suggesting that what we call the beginning was merely a turning point in an infinite cosmic dance. Here's how it works. In Einstein's general relativity, the Big Bang emerges as a point of infinite density where the laws of physics break down. But loop quantum gravity, which treats space itself as a woven fabric of tiny, discrete loops, prevents this collapse. Picture space as a mesh so fine that it can't be squeezed to infinity, like a sponge that resists being crushed beyond a certain point. When the universe contracts, it reaches a minimum size, then bounces back outward in a cosmic rebound. No singularity, no nothingness before, just an eternal oscillation between expansion and contraction. The evidence for this isn't purely theoretical. Strange anomalies in the cosmic microwave background, the afterglow of the early universe, hint at scars from a pre-Big Bang phase. Some patterns in this primordial light appear too uniform, as if smoothed by an earlier era of collapse. It's like finding fingerprints on a mirror that suggest someone wiped it clean before you walked in. Even more tantalizing, certain mathematical models of loop quantum gravity predict subtle imprints in the universe's large-scale structure that we might one day detect. Critics argue that the bounce remains speculative, lacking the smoking gun evidence of, say, gravitational waves from inflation. But supporters counter that avoiding a singularity isn't just elegant, it's necessary. Singularities are where physics gives up and science thrives on explanations, not dead ends. A cyclic universe also sidesteps the thorny "why is there something" rather than nothing question by making existence a perpetual given. Think about the implications. If the universe cycles endlessly, every configuration of matter and energy will eventually recur. Given enough time, every atom in your body might one day reassemble in the same arrangement, not once, but an infinite number of times across endless cosmic cycles. It's a dizzying thought, time without end, universes without limit, and a reality where endings are just new beginnings in disguise. What if everything you see, touch, and experience, every star, every planet, even your own thoughts, is nothing more than a projection, a shimmering hologram cast from the edge of reality? This isn't the plot of a sci-fi movie, it's the holographic principle, a theory so radical it suggests our three-dimensional universe might be a shadow of a two-dimensional code written on the cosmic horizon. The idea didn't spring from wild speculation, but from one of the most mysterious objects in existence, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. Black holes have entropy, a measure of disorder that implies they carry hidden information. But here's the twist: that information doesn't seem to reside inside the black hole. Instead, it's etched onto its surface, the event horizon, like data encoded on a celestial hard drive. Years later, Leonard Susskind and Gerard T. Hooft took this further, proposing that if a black hole's interior can be described entirely by its surface, maybe the entire universe operates the same way. Picture a movie screen. The images appear three-dimensional, but every detail comes from flat pixels. In this view, spacetime isn't the foundation of reality. It's an illusion, a hologram generated by quantum bits dancing on a distant, two-dimensional boundary we can't see. The implications are staggering. If the holographic principle holds, the universe isn't just in space and time. It's built from information, like a cosmic simulation running on a flat surface trillions of light years away. Every event, every particle collision, every thought you've ever had would just be a fragment of this vast, interconnected code. It's as if we're living inside a grand cosmic mirage where depth and solidity are tricks of the light. But how could this possibly work? Think of a credit card hologram tilted, and the image seems to move in three dimensions, even though it's just light interacting with microscopic grooves. The holographic principle suggests spacetime behaves similarly, with gravity and quantum fields emerging from entangled bits of information on a lower dimensional surface. Some versions of the theory even propose that our universe's boundary isn't far away, it's all around us, at the limits of the observable cosmos. We're not just looking at a hologram, we're inside one. Critics argue the math is still speculative, and no experiment has yet confirmed the principle applies beyond black holes. But supporters point to strange alignments in theoretical physics, like how equations describing the universe's bulk perfectly match those describing its boundary. It's as if the universe keeps leaving clues that we're all part of a grand projection. And if that's true, the very nature of reality might be far stranger, far more interconnected than we ever imagined. After all, in a holographic universe, every atom in your body is just a pixel in a cosmic image, one that stretches to the very edges of existence. If space and time are the universe's stage, then quantum entanglement might be the hidden puppeteer pulling all the strings. This isn't just a poetic metaphor, it's a cutting-edge theory that suggests the very fabric of reality is stitched together by spooky connections between particles, bonds so profound they defy distance, logic, and even our understanding of cause and effect. Imagine two coins flipped on opposite sides of the galaxy, landing on the same face every single time without any signal passing between them. That's entanglement in action, a phenomenon Einstein famously dismissed as spooky action at a distance, but one that's been proven in labs again and again. Now, physicists are asking an even wilder question: what if entanglement isn't just a quantum quirk, but the cosmic glue holding spacetime itself together? At the heart of this idea is the ER=EPR conjecture, a proposal so elegant it ties two of physics' greatest puzzles into one. ER refers to Einstein-Rosen bridges, better known as wormholes, theoretical tunnels through spacetime. EPR stands for Einstein-Podolsky-Rosen, the trio who first highlighted entanglement's weirdness. The conjecture suggests these aren't separate phenomena but two sides of the same coin. Entangled particles might be connected by microscopic wormholes, weaving space itself into a vast, interconnected web. Picture the universe as a tapestry where every thread is a quantum link and every knot is a hidden shortcut through the cosmic fabric. It's a vision where the empty space between stars isn't empty at all, but seething with invisible connections that bind everything together. The implications are staggering. If entanglement builds spacetime, then the universe isn't just expanding, it's growing new quantum links like a living network. Black holes, often seen as cosmic dead ends, might instead be entanglement hubs, their event horizons buzzing with connections to other points in space or even other universes. Even gravity, the force that sculpts galaxies, could emerge from this deeper layer of quantum ties. Think of it like the pixels on your screen. What looks like a smooth image is really countless tiny dots working together. Similarly, the smooth geometry of spacetime might be a collective illusion emerging from countless entangled quantum events. Experiments are already testing these ideas. Researchers have simulated wormhole-like behavior using entangled quantum systems, creating lab-scale models of how spacetime might function. Others study the holographic principle, which suggests entanglement entropy, a measure of quantum connections, could literally carve out the dimensions we experience. It's as if we're detectives reconstructing a crime scene, piecing together clues to uncover a reality far stranger than we ever imagined, but not everyone's convinced. Skeptics argue that while entanglement is real, scaling it up to explain the universe's structure is a leap. Wormholes, if they exist, are likely unstable, collapsing before anything could traverse them. And without a full theory of quantum gravity, we're still missing the rulebook for how these pieces fit together. Yet the math keeps hinting at something profound. When black holes entangle, do they create new spacetime? Can we someday manipulate entanglement to probe the universe's seams? One thing's certain: if this theory holds, the cosmos is far more intimate than it appears. Every atom in your body might be subtly linked to distant quasars, ancient supernova, or even other versions of reality. The night sky wouldn't just be a collection of isolated stars, but a shimmering network of quantum handshakes, whispering the universe's deepest secrets across the void. What if the universe isn't real, at least not in the way we think? Not as a cosmic accident or a divine creation, but as an intricate simulation, a universe-sized quantum computer humming away in some higher reality. This is the simulated universe hypothesis, a theory that blurs the line between science and science fiction until you look at the math. At its core lies a provocative question: if advanced civilizations could one day create hyper-realistic simulations of consciousness and physics, what's stopping us from already living inside one? The argument starts with numbers. Our universe runs on equations so precise they border on eerie. The constants of nature, gravity, electromagnetism, the strength of nuclear forces, are dialed to values so exact that even slight changes would make life impossible. It's as if the cosmos was fine-tuned by a programmer optimizing their code. Even stranger, quantum mechanics behaves suspiciously like a rendering engine. Particles only snap into definite states when observed, as if the simulation conserves processing power by filling in details only when needed. Think of a video game that only renders the parts of the world you're looking at. Now imagine that principle applied to reality itself. But here's the twist. Proponents like Nick Bostrom argue that if civilizations ever reach the technological stage where they can simulate conscious minds, the number of simulated beings would vastly outnumber biological ones. Statistically, the odds tilt heavily toward us being among the simulations. It's like realizing that for every real person on Earth, there are billions of characters in video games. Odds are you're not the player holding the controller. Quantum computing adds fuel to the fire. Today's fledgling quantum machines exploit superposition and entanglement to perform calculations impossible for classical computers. If we're already glimpsing this power, what could a civilization millions of years ahead achieve? A mature quantum simulator might not just model a universe, it could become one, with every particle interaction calculated in a self-consistent way. Yet critics pounce on the holes. Simulations require energy and hardware, but our universe shows no signs of computational limits, no lag, no pixelation, no out-of-memory errors at the edges of black holes. And if this is a simulation, who's running it? Another simulated civilization in an infinite regression. Some physicists counter that a truly advanced simulator wouldn't need physical hardware as we know it. It might harness quantum fields or spacetime itself as its operating system. The debate gets even stranger when you consider glitches or their absence. If reality is a construct, why don't we see signs of corners being cut? Some suggest quantum indeterminacy is the glitch, the simulation's way of handling uncertainty. Others point to unexplained anomalies in cosmic rays or mathematical constants as potential artifacts, like cosmic typos in the code. Whether the theory holds or not, it forces a profound shift in perspective. If we're living in a simulation, the quest to understand quantum mechanics isn't just science, it's reverse engineering the universe's source code. And if we're not, the mere fact that the math allows this possibility hints at a reality far more malleable, far more mysterious than we ever dared to suspect. After all, in a cosmos where particles can be in two places at once, who's to say the whole thing isn't just an elaborate calculation running on some unimaginable machine? Imagine a universe that doesn't begin with a bang but with a whisper. That's the radical vision of Roger Penrose's conformal cyclic cosmology, a theory so audacious it rewrites the cosmic timeline into an endless loop of rebirth. While most models treat the Big Bang as a definitive starting point, Penrose proposes something far stranger. Our universe is just one chapter in an infinite book, where the death of one cosmos becomes the birth of another. The key to this cosmic recycling, black holes, not as destroyers but as architects of new realities. Here's how it works. In the far, far future, the universe will expand into cold, empty darkness, with all matter eventually consumed by black holes. But according to Penrose, this bleak heat death isn't the end. As black holes evaporate over eons via Hawking radiation, they leave behind a universe devoid of scale, a featureless expanse where space and time lose all meaning. In this state, called conformal invariance, the universe resets. The infinite future of one cycle becomes the singularity of the next, birthing a new Big Bang from the ashes of the old. It's like a phoenix rising, except instead of fire, the transformation hinges on the universe forgetting its own size. But how could we possibly find evidence for such a mind-bending idea? Penrose points to the cosmic microwave background, the afterglow of the Big Bang. Buried in this faint radiation, he claims, are mysterious hotspots called Hawking points, imprints of supermassive black holes from a previous eon. These points would be the dying screams of ancient black holes, their final bursts of Hawking radiation etched into the fabric of the next universe like cosmic graffiti. To skeptics, these patterns might just be statistical flukes, but Penrose and his collaborators argue their distribution matches predictions eerily well, as if the universe left breadcrumbs for us to follow. Critics counter that the math is speculative and alternative explanations for the CMB anomalies exist. After all, the standard Big Bang model doesn't require ghostly echoes from other universes. Yet there's poetic symmetry in Penrose's vision. If black holes, those ultimate cosmic shredders, are also the seeds of new beginnings, it suggests a universe that's far more resilient, far more cyclical than we ever imagined. No creator, no absolute beginning, just an infinite dance of collapse and renewal. And here's the deepest implication. If conformal cyclic cosmology is true, time itself might be an illusion. Each cycle's end seamlessly blends into the next start, making the distinction meaningless. There's no first universe, no final one, just an endless now stretching forever in both directions. It's a humbling thought. Everything we see, from the farthest galaxy to the phone in your hand, could be one fleeting note in a symphony that's been playing forever, and will keep playing long after our chapter fades to black. If you could shrink down to a size trillions of times smaller than an atom, you might catch a glimpse of the universe's hidden blueprints, not in the 3 dimensions we know, but curled up in tiny, intricate folds of reality. This is the realm of string theory, where the fundamental building blocks of existence aren't particles but vibrating strings, and where the fabric of space has not just length, width, and depth, but 6 extra dimensions twisted into shapes so complex they're called Calabi-Yau manifolds. These hidden folds aren't science fiction. They're a serious proposal for how the universe might have engineered its own birth, with quantum vibrations in these extra dimensions sparking everything into being. Picture a guitar string vibrating at different frequencies to produce distinct musical notes. In string theory, the universe works similarly. Each vibration pattern corresponds to a different particle. An electron might be one note, a quark another, but here's the catch. These strings don't dance in the 3-dimensional space we're used to. They move through a 10-dimensional arena, with 6 dimensions coiled so tightly they're invisible to us, like the grooves on a vinyl record too fine for the naked eye to see. The shape of these extra dimensions isn't arbitrary. It's sculpted by the strings themselves, determining the laws of physics we observe. A slight twist in a Calabi-Yau shape could mean gravity is stronger, electrons heavier, or the universe never forming stars at all. This leads to the landscape problem, one of string theory's most controversial puzzles. The math suggests there aren't just a few possible shapes for these extra dimensions. There are around 10 to the power of 500 variations. That's a 1 followed by 500 zeros, a number so vast it dwarfs the atoms in the observable universe. Each version represents a different universe with its own physics, its own constants, its own potential for life. Our cosmos, then, might just be one accidental arrangement in an unfathomable sea of possibilities. Critics argue this makes string theory untestable. If any outcome is possible, how can we prove it's right? Supporters counter that this very vastness might explain why our universe is finely tuned for existence. In an infinite landscape, some corners were bound to get lucky. Testing these ideas isn't easy, but not impossible. Some physicists hunt for subtle imprints extra dimensions might leave on gravitational waves or high-energy particle collisions. Others look for cosmic strings, ancient defects in spacetime that could be fossilized remnants of the early universe's dimensional origami. There's even a wild possibility that if we could harness enough energy, we might briefly uncurl a dimension, like stretching a coiled spring to glimpse its hidden loops. The most startling implication: if string theory is correct, the Big Bang wasn't just an explosion. it might have been a dimensional unraveling, a moment when all 10 dimensions flared into existence before 6 of them collapsed into hiding. What we call the beginning could have been a cosmic metamorphosis, with the universe's quantum origins written in geometry we're only beginning to decipher. In this view, reality isn't just built on particles or forces, but on hidden mathematical shapes vibrating in the dark, a symphony of dimensions playing the oldest song in existence. At the heart of quantum mechanics lies one of science's most unsettling questions. Does reality even exist when we're not looking? The Copenhagen interpretation suggests that particles exist in a haze of probabilities until measured, collapsing into definite states only when observed. But what if this isn't just a microscopic quirk? What if the act of observation played a starring role in the universe's birth? Enter quantum Darwinism, a theory proposing that the quantum weirdness of the early cosmos didn't just fade away. It was selected for stability, like a cosmic survival of the fittest. Think of the universe's first moments as a quantum soup, where every possible configuration of particles flickered in and out of existence. Most of these configurations were chaotic, unstable, vanishing as quickly as they appeared. But a handful of states were robust enough to be repeatedly observed, not by humans, but by their own environment. Photons scattering off atoms, gravitational interactions, even random fluctuations could act as rudimentary observers, reinforcing certain quantum states while others faded into oblivion. Over time, these stable states became the classical reality we recognize, not because they were the only possibilities, but because they were the only ones that could stick around long enough to matter. It's like a room full of whispering voices where only the loudest, clearest phrases get passed on until they're all anyone remembers. This leads to a jaw-dropping implication. The universe we see might just be the version that survived a quantum selection process, its laws and constants frozen into place because they were the most observable, the most shareable configurations. But here's where it gets thorny. If observation shapes reality, what counts as an observer? The Wigner's friend thought experiment lays bare the paradox. Imagine a scientist in a lab measuring a quantum particle, collapsing its wave function. But to another scientist outside the lab, the first scientist and the particle are still in superposition until they peek inside. Who's right? The unsettling answer: both, until their realities decohere. Apply this to cosmology, and you're left with a chicken and egg problem. Did observers emerge from the universe, or did the universe emerge from observation? Some theorists take this even further, suggesting that conscious observers, not just environmental interactions, might play an irreducible role in shaping reality. It's a controversial stance, often dismissed as anthropocentrism dressed in equations. After all, the cosmos existed for billions of years before life appeared. But proponents argue that retrocausality, effects preceding causes, could weave consciousness into the universe's foundation. Picture a painting that only solidifies into existence when someone looks at it, except the someone is the painting's own future. Critics counter that quantum Darwinism doesn't need consciousness to explain classical reality. Decoherence theory shows how quantum states lose coherence through environmental interactions, no observers required. Yet the question lingers: is decoherence just a mathematical convenience, or does it hint at a deeper truth about how reality crystallizes from possibility? Whether you lean toward pragmatism or philosophy, one thing's certain: the universe seems to favor stories that can be told, states that can be seen. And in that preference, we might just find the fingerprints of our own cosmic origins. There's a theory lurking in the equations of quantum physics so unsettling, it makes black holes look tame by comparison. It suggests that at any moment, without warning, the universe could rewrite its own rulebook, not through some cosmic accident, but because our entire existence might be built on a lie. This is vacuum decay, the nightmare scenario where the fabric of reality itself turns out to be less stable than we imagined, and the ground beneath our feet isn't solid ground at all, but thin ice over an abyss. To understand this existential threat, we need to examine the Higgs field. You've probably heard of the Higgs boson, the so-called God particle, discovered at CERN in 2012. But the real star of the show is the invisible energy field that permeates all of space, giving particles their mass like cosmic molasses. What keeps this field stable is a delicate balance, like a pencil perfectly balanced on its tip. The terrifying part, our universe's Higgs field might not be in its lowest possible energy state, meaning we're living in what physicists call a false vacuum, a temporary configuration that could, at any moment, drop into a more stable but utterly alien state. Imagine a valley surrounded by mountains with our universe sitting comfortably in a high meadow. It looks stable, but there's a deeper valley hidden beyond the peaks, one with different physical laws. All it would take is one quantum nudge, one random fluctuation, to send us tumbling over the ridge. Once started, this decay would race outward at the speed of light, rewriting the fundamental constants of nature as it goes. Atoms might dissolve, gravity could reverse, or the very concept of matter might cease to have meaning. The worst part, we wouldn't see it coming until it hit us. There's no warning, no flash of light, just a sudden and irreversible transformation of reality itself. Here's where it gets weirder. Some calculations suggest this process might have already begun somewhere in the cosmos. A bubble of true vacuum could be expanding toward us right now, its wall of annihilation too distant to detect. The universe is so vast that such a bubble might take billions of years to reach us, or it might be just beyond the edge of the observable universe, forever out of sight but never out of mind. Not everyone buys this doomsday scenario. The standard model calculations predicting Higgs instability assume no new physics beyond what we've discovered, a big if. Some supersymmetry theories suggest unknown particles could stabilize the vacuum. Others argue that the universe's accelerated expansion might prevent decay bubbles from ever reaching us. But the haunting possibility remains. Our reality might be the cosmic equivalent of a house built on sand, its foundations less certain than we dare admit. What makes vacuum decay uniquely chilling isn't just the scale of destruction, it's the idea that physics itself could change. This isn't an asteroid impact or a supernova, it's a rewriting of the universe's source code. The speed of light, the strength of gravity, the very rules that let stars shine and life exist might all be temporary glitches in a grander, stranger scheme we don't yet understand. The cosmos might not just be stranger than we imagine, but stranger than we can imagine. And our version of reality could be just one temporary arrangement in an infinite series of possibilities, as fleeting as a soap bubble in the quantum void. What if time, the steady tick of the universe's clock, isn't real? Not in the way we experience it, at least. Carlo Rovelli's thermal time hypothesis flips our intuition on its head, suggesting that time isn't a fundamental backdrop to reality but a shimmering illusion, a side effect of quantum relationships playing out beneath the surface. Picture a movie projected on a screen. We see motion, change, a flowing narrative, but strip away the frames and all you have are static images. Time, in this view, might be just like that movie, a story our brains stitch together from deeper, timeless quantum processes. This idea isn't just philosophical wordplay. Rovelli's work in loop quantum gravity suggests that at the most basic level, the universe doesn't evolve in time, it creates time through interactions. Think of a vast cosmic network where quantum events only define their own local sense of before and after relative to one another. There's no universal clock ticking away in the background. Instead, time emerges like temperature emerging from the frenetic dance of atoms. A single atom doesn't have a temperature, but a collection of them does. Similarly, individual quantum events might not experience time, but their collective behavior gives rise to the flow we perceive. The implications for the Big Bang are staggering. If time isn't fundamental, then the singularity wasn't a moment in time, it was a boundary of time, a place where our usual notions of past and future break down entirely. Asking what happened before the Big Bang becomes as meaningless as asking what's north of the North Pole. Instead, the early universe might have been a timeless quantum foam, with time itself crystallizing as particles began interacting in complex ways. It's as if the universe had to wake up to the idea of time, emerging groggily from a dream of pure potential. Critics raise valid questions. If time is emergent, why does it feel so uniform? Why does the arrow of time always point toward entropy? Ravelli's answer ties time to thermodynamics. The so-called thermal time flows in the direction of increasing disorder because that's how quantum correlations propagate. It's not that entropy increases over time, it's that our perception of time is entropy's increase, a cosmic gradient we're helplessly sliding down. This reshapes our understanding of reality in ways both subtle and profound. Black holes, where gravity warps time to a standstill, might not be freezing time. They could be regions where the quantum interactions that generate time become too sparse to sustain the illusion. Even quantum entanglement, with its spooky, instantaneous connections, makes more sense if time is a local phenomenon rather than a global stage, the most beautiful part. This theory doesn't just demote time, it elevates relationships. Reality isn't a collection of things existing in time and space. It's a web of events whose connections define time and space. The universe isn't happening in time, it's happening because of these quantum handshakes, with every interaction whispering, now. And in that whisper, we might just hear the echo of our own cosmic origins. Black holes aren't just cosmic vacuum cleaners, they might be cosmic wombs. That's the provocative claim of black hole cosmology, a theory suggesting our entire universe exists inside a black hole, nested like a Russian doll within some grander reality. At first glance, it sounds like fantasy, but the parallels between black hole physics and the Big Bang are too striking to ignore. Both feature singularities, points of infinite density where known physics breaks down. Both generate immense spacetime curvature, and both mark boundaries where time itself behaves in ways we barely comprehend. So what if they're not just similar but the same? Picture a black hole forming in some higher dimensional universe. As matter collapses inward, it doesn't just vanish, it could undergo an extreme transformation, rebounding as an expanding fireball on the other side of the event horizon. To an outside observer, the black hole is a dark, frozen relic, but to anything inside, it's a newborn universe inflating rapidly as if from a Big Bang. In this view, every black hole in our cosmos might contain its own universe, and our own reality could be the interior of one such object in a grand cosmic chain. The idea isn't entirely new. Physicist Roj Pathria explored it in the 1970s, and Nikodem Poplawski later refined the math using torsion-based gravity models. Here's where it gets wild. This theory could solve one of cosmology's biggest puzzles, dark energy. The mysterious force accelerating the universe's expansion might simply be the gravitational pull of the parent universe outside our black hole's event horizon. Imagine you're in a falling elevator. You'd feel weightless, not because gravity's gone, but because you're in free fall. Similarly, our universe's accelerating expansion might be a kind of cosmic free fall, with external gravity stretching spacetime from beyond the veil we can't see. Skeptics highlight the gaps. Black hole interiors are notoriously hostile spaghettification, crushing tides, chaotic singularities, hardly the smooth, isotropic cosmos we observe. But proponents argue that a rotating black hole's inner structure could avoid these extremes, creating a more hospitable environment. Others question how information could pass from the parent universe to ours, though some models suggest quantum entanglement might thread the needle, preserving subtle links across the event horizon. The most mind-bending implication: if every black hole births a universe, then universes might replicate like cosmic DNA, with each generation inheriting tweaked physical constants from its parent. Our finely tuned laws of physics wouldn't need a multiverse to explain them, just an evolutionary chain of universes. each forged in the heart of a black hole, each testing new variations until life-friendly conditions emerge. It's a vision where black holes aren't tombs, but nurseries where death in one reality becomes birth in another, and the cosmos endlessly reinvents itself in an infinite dance of collapse and creation. What if quantum randomness isn't random at all? While most physicists accept that particles behave unpredictably, popping into existence here or there with no underlying cause, pilot wave theory dares to suggest otherwise. This radical alternative, also called Bohmian mechanics, claims the quantum world is as deterministic as clockwork, with every particle guided by hidden forces we simply haven't uncovered yet. Imagine a surfer riding a wave. From above, their path might seem chaotic, but beneath the surface, invisible currents steer every move. Pilot wave theory argues reality works the same way, with a secret layer of physics pulling the strings. The idea dates back to the 1920s, when quantum mechanics was still taking shape. While giants like Bohr and Heisenberg embraced probability, physicist David Bohm proposed a startling alternative. Particles have definite positions at all times, guided by a pilot wave that orchestrates their motion. In this view, the famous double-slit experiment where particles act like waves when unobserved isn't proof of inherent randomness. Instead, the pilot wave interacts with itself, creating interference patterns that look probabilistic, even though every particle follows a precise, predetermined path. It's as if cars on a highway were invisibly tethered to rails, their seemingly free motion actually choreographed down to the millimeter. For decades, Bohm's theory was dismissed as a philosophical curiosity. Then, in 2005, a breakthrough experiment brought it roaring back into contention. Researchers discovered that oil droplets bouncing on a vibrating fluid could eerily replicate quantum behavior, forming interference patterns, tunneling through barriers, even orbiting each other like electrons in an atom. These walking droplets weren't probabilistic. Their paths were clearly guided by waves they generated in the fluid. The implications were staggering. Could the quantum world operate similarly, with particles surfing hidden waves we can't yet detect? Mainstream quantum theory has fierce counter-arguments. Hidden variables like Bohm's pilot wave struggle to explain quantum entanglements, instantaneous correlations without violating relativity's cosmic speed limit. Bell's theorem seemed to slam the door on local hidden variables, yet Bohm's model survives by being non-local. Its pilot wave connects particles across vast distances, a feature some call action at a distance in disguise. Critics also note the theory's mathematical complexity. It reproduces quantum predictions but adds layers of unobservable machinery. Why embrace a more convoluted model if it doesn't yield new testable results? Supporters fire back with elegance. Pilot wave theory banishes the measurement problem, no collapse of the wave function needed, and restores determinism to a realm where science had surrendered to chance. Recent extensions even apply it to quantum field theory and cosmology, suggesting the early universe's fluctuations might have been sculpted by deterministic waves rather than quantum dice rolls. If true, the Big Bang wasn't a random bounce but the unfolding of a deeply ordered process, with every galaxy, star, and atom following a script written in hidden physics. The debate is far from settled, but pilot wave theory's resurgence proves a vital point. Quantum mechanics might not be the final word. Beneath the apparent chaos of the subatomic world, there could be rhythms we're only beginning to hear, a cosmic symphony playing just beyond the range of our current instruments. Whether Bohm's vision holds up or not, it challenges us to look deeper, to question whether the universe's quantum origins are as mysterious as they seem, or if we've simply been missing the hidden currents guiding the dance. Zoom in far enough, past atoms, past quarks, past anything we've ever observed, and the smooth fabric of spacetime might dissolve into a seething, chaotic froth. This is the realm of quantum foam, where the universe's most fundamental structure isn't a tidy grid of space and time, but a turbulent sea of bubbles flickering in and out of existence at scales a billion times smaller than an atom. If this idea sounds surreal, that's because it defies everything we experience. Yet, according to quantum gravity theories, this foam could be the primordial soup from which our entire universe emerged, not with a bang, but with a trillion infinitesimal quantum shudders. Picture spacetime not as a static stage, but as a dynamic, living thing. At the Planck scale, where distances are so tiny that measuring them would require energies strong enough to create black holes, gravity and quantum mechanics wage an endless tug of war. Tiny regions of space might momentarily warp into microscopic black holes, only to evaporate instantly. Wormholes could thread through the foam like transient stitches, connecting points in spacetime for mere fractions of a second. Even causality, the bedrock of reality, might falter here, with effects sometimes preceding causes in a dizzying quantum dance. This isn't empty space, it's space at its most alive, bubbling with potential. Now stretch this vision back to the universe's first moments. Instead of a singularity, imagine a vast quantum foam, its fluctuations growing more violent as energy density skyrockets. Most bubbles collapse back into nothingness, but a rare few, through random chance or some hidden physics, expand rapidly, inflating into entire universes. Our cosmos, then, might be one such bubble that escaped annihilation, a cosmic lottery winner whose expansion outpaced the foam's turbulence. It's as if the universe didn't begin with an explosion, but with a whisper, a quantum hiccup amplified into existence. The math behind this is both elegant and thorny. Quantum foam emerges naturally when theorists try to merge Einstein's general relativity with quantum mechanics. In loop quantum gravity, spacetime isn't infinitely divisible, it's woven from discrete loops, giving the foam a granular structure. String theory, meanwhile, suggests the foam's bubbles could be higher dimensional brains colliding or vibrating in hidden dimensions. But the real challenge is testing these ideas. How do you observe something that vanishes in a flash, existing at scales beyond our most powerful particle colliders? Some clues might lie in cosmic rays. Ultra-high-energy particles traveling across the universe could interact with the foam's microscopic structure, leaving subtle fingerprints in their arrival patterns. Others hunt for blurring in distant gamma-ray bursts, hints that spacetime's frothiness slightly scrambles light over vast distances. Even more radically, some propose that if we could probe the singularity inside a black hole, we might find not infinity, but the universe's original quantum foam, frozen in time like a cosmic fossil. Critics argue the foam remains a mathematical abstraction, untethered from observable reality. Without experimental proof, it risks becoming a modern ether, a placeholder for our ignorance. Yet supporters counter that ignoring quantum foam is like denying atoms because they couldn't be seen in the 19th century. The foam isn't just a quirky idea, it's a necessary consequence of taking quantum gravity seriously. And here's the profound implication. If spacetime is foamy at its core, then the universe isn't built on a foundation of rigid laws, but on a quantum casino where probabilities rule. The Big Bang wasn't an absolute beginning, just a statistical fluctuation in an eternal, frothy sea. In this view, reality is less a grand symphony and more a jazz improvisation, with spacetime itself as the instrument, playing notes we're only beginning to hear. Imagine a universe where creation never stops, not just one big bang, but an endless fireworks display of cosmic births, each sparking new realities with their own laws of physics. This is eternal inflation, a theory so expansive it makes the multiverse seem cramped by comparison. At its heart lies a simple but staggering idea. The vacuum of space isn't empty, but brimming with potential energy, a quantum field so unstable it constantly erupts into new universes like bubbles in a boiling pot. And here's the twist: our entire cosmos might just be one lucky bubble in an infinite froth of others, each forever out of reach, yet potentially leaving traces of their existence in the oldest light we can see. The mechanism works like this. In the instant after the Big Bang, space may have undergone a period of hyper-expansion called inflation, stretching smaller than an atom to larger than the observable universe in a fraction of a second. Most inflation models suggest this process ended when the inflationary field decayed, releasing its energy as matter and radiation, the hot soup of our early cosmos. But eternal inflation proposes something wilder. While most regions of space stop inflating, others keep expanding exponentially, creating pockets where inflation never ends. These regions spawn new bubbles, new universes, each with their own physics, like soap bubbles forming in an ever-growing foam. The math is startlingly robust. Once inflation starts in certain quantum field configurations, it becomes self-sustaining, birthing universes faster than light can cross them. Now, the million-dollar question. If these bubble universes are forever hidden beyond our cosmic horizon, how could we ever prove they exist? Some theorists point to the cosmic microwave background, the afterglow of the Big Bang, as a potential treasure map. When bubbles form close enough to collide, the impact could leave faint bruises in this primordial light, circular patterns of temperature variations that defy standard inflation's predictions. It's like listening for echoes of a conversation happening in another room. The walls might muffle the words, but the vibrations could still reach us. The hunt for these signatures is already underway. Astronomers have scoured the CMB for anomalous rings or gradients, with some claiming tentative detections. One controversial study identified 4 strange circular patches in the data, each far larger than any known astrophysical process could explain. Skeptics argue these could be statistical flukes or artifacts of galactic dust, but supporters counter that their size and symmetry align eerily well with bubble collision models. The debate rages, but the mere possibility is electrifying. We might be staring at scars from a primordial clash between our universe and another, a cosmic fist bump frozen in time. Critics, though, highlight the theory's slippery nature. If bubble universes are inherently separate, forever receding beyond the reach of light due to eternal inflation's breakneck expansion, can we ever gather conclusive evidence? Some argue that without falsifiability, eternal inflation strays into philosophy. Others fire back that absence of evidence isn't evidence of absence after all. We once thought the atom was indivisible until we built tools to crack it open. Future CMB experiments with unprecedented sensitivity, like the proposed CMB S4 project, could settle the debate by either confirming anomalous patterns or ruling them out entirely. Even if we never detect a collision, the theory's implications are profound. Eternal inflation doesn't just suggest a multiverse, it demands one, endlessly generating diversity on scales beyond comprehension. In this view, our finely tuned constants aren't miracles. They're inevitabilities, statistical certainties in an infinite ensemble where every possible configuration exists somewhere. The universe isn't a one-off masterpiece, but a single brushstroke in an ever-expanding canvas. Its structure less a grand design and more a quantum roll of the dice. And that might be the most humbling idea of all. We're not special, just lucky residents of a bubble that, against incalculable odds, got the physics just right for us to sit here pondering the bubbles beyond. John Wheeler's vision of reality is so radical it upends the very definition of existence. The legendary physicist proposed that the universe isn't just governed by information, it's made of it, with every particle, force, and law emerging from a cosmic game of quantum questions and answers. He called this it from bit, the idea that every tangible thing we see ultimately boils down to bits, the yes or no choices etched into the fabric of reality by observation. But here's where it gets surreal. Wheeler argued that the universe only solidifies into being when observed, meaning the past isn't just fixed history. It's a story still being written, with present-day measurements reaching back to shape what came before. Take the infamous delayed choice experiment, a quantum twist on the classic double-slit setup. When particles are fired at a barrier with two slits, they behave like waves if no one watches which slit they pass through, creating an interference pattern on the far side. But if you place detectors at the slits to catch them in the act, they suddenly switch to behaving like particles. Wheeler's genius was asking, what if we delay that choice until after the particle has already passed through? Astonishingly, the results hold the particle's behavior changes retroactively, as if future observation rewrites its past. It's like a detective altering a crime scene by deciding, after the fact, where to look for fingerprints. This isn't just a quantum parlor trick. If observation defines reality, then the universe might be a self-excited circuit, a loop where the act of measurement brings the cosmos into sharper focus with each interaction. Picture a cosmic game of 20 questions, where the universe only crystallizes answers as we ask, except the questions and answers are entangled across time, with future queries shaping ancient events. In Wheeler's participatory universe, the Big Bang didn't just happen 13.8 billion years ago. It's still happening, its details contingent on every observation made since. Critics bristle at the implied solipsism. Does this mean nothing existed before conscious observers? Wheeler sidestepped the trap by broadening observation to include any quantum interaction, from a photon hitting a rock to a black hole swallowing starlight. Reality isn't conjured by human minds, but by the ceaseless exchange of quantum information, a cosmic dialogue where even dust particles ask and answer through entanglement. The most electrifying implication: if the past is malleable to quantum measurement, then time itself might not flow in one direction. Retrocausality, future events influencing the past, could be woven into physics at the deepest level. Imagine planting a tree today whose roots somehow anchor a forest that existed 1,000,000 years ago. In Wheeler's vision, the universe isn't a pre-recorded film, it's a live broadcast with edits propagating backward and forward through time. Whether his participatory universe holds up or not, it forces a seismic shift in perspective. We're not passive witnesses to reality, we're co-authors, our observations stitching the cosmic tapestry one quantum bit at a time. And somewhere in that entanglement of questions and answers, the universe might just be whispering its deepest secret. Existence isn't something you find. It's something you make. If the universe lasts long enough, something even stranger than black holes or quantum foam might emerge, not from stardust or evolution, but from pure, mindless chaos. These are Boltzmann brains, hypothetical self-aware entities that could, statistically speaking, spontaneously assemble from random quantum fluctuations in the void. Picture a single conscious mind popping into existence amidst an endless sea of darkness, complete with false memories of a past that never happened, convinced it's a human sitting on a planet it never actually inhabited. This isn't just sci-fi, it's a nightmarish puzzle at the crossroads of physics and philosophy, one that threatens to unravel our most basic assumptions about reality. The idea traces back to Ludwig Boltzmann, the 19th century physicist who linked entropy to probability. In an infinitely old or infinitely large universe, even the most improbable events must happen eventually, including the accidental assembly of a fully functioning brain. Given enough time, atoms jostling in the void could randomly align into a thinking, self-aware structure, complete with fabricated sensory input convincing it that it's part of a coherent world. The terrifying implication: if Boltzmann brains are statistically inevitable, then for every real observer like us, there could be countless disembodied minds hallucinating existence in the cosmic abyss. And if that's true, how can we trust that we're not just Boltzmann brains momentarily coherent before dissolving back into chaos? Cosmologists recoil at this scenario not because it's unsettling, but because it breaks science's predictive power. If random, self-aware fluctuations outnumber real observers, then any cosmological model predicting them becomes useless. Imagine flipping a coin 1,000,000 times and always getting heads. not because the coin's unfair, but because you're statistically likelier to be a hallucination of someone flipping heads than an actual observer in a fair coin universe. That's the Boltzmann brain paradox. It turns fundamental physics into a house of mirrors where nothing can be trusted, not even the data we use to test theories. Some physicists dismiss the problem as a reductio ad absurdum, a sign that our models of eternal universes or quantum fluctuations are missing something critical. Maybe the universe isn't infinite or eternal enough for Boltzmann brains to dominate. Others argue that consciousness might require more than just the right atomic arrangement. Perhaps self-awareness needs a substrate of continuity, something fleeting fluctuations can't provide. Then there's the anthropic answer. We clearly exist in a structured cosmos, so any theory making Boltzmann brains probable must be flawed. It's like waking up in a well-built house and concluding you're probably a hallucination, when the simpler explanation is that houses and you are real. Yet the haunting possibility lingers. If quantum mechanics allows particles to appear from nothing, and entropy drives the universe toward disorder, what's stopping fragments of awareness from coalescing in the dark? The answer might lie not in physics alone, but in the nature of consciousness itself, a frontier where science still stumbles in the dark. For now, Boltzmann brains remain a ghost in the equations, a reminder that the universe's quantum origins could be far stranger, far more absurd than even our wildest theories dare to suggest. Hidden in the equations of particle physics is a mathematical symmetry so perfect it would rewrite the cosmic rulebook, if only we could find it. Supersymmetry, or SUSY for short, proposes that every known particle has a secret twin, a superpartner waiting in the wings of reality. These shadow particles aren't just duplicates, they're the universe's balancing act, stepping in to solve mysteries ranging from the fragility of the Higgs field to the missing mass of dark matter. But here's the catch. Decades of hunting at the Large Hadron Collider have turned up empty-handed, leaving physicists to wonder, did we get the math wrong, or are we just looking in the wrong way? Think of supersymmetry as a cosmic mirror. For every Fermion particles like electrons and quarks that make up matter, there should be a boson superpartner carrying force. And for every boson like photons or gluons, there ought to be a fermion twin. This elegant pairing would smooth out the jagged edges of quantum theory, explaining why gravity is so weak compared to other forces, and why the Higgs boson's mass doesn't get obliterated by quantum corrections. Imagine building a house where every beam has a counterbalance. No matter how strong the wind the structure holds, SUSY offers that stability to the universe itself, ensuring the delicate constants we rely on don't collapse under their own weight. Yet the LHC's silence is deafening. After smashing protons together at energies that should have conjured supersymmetric particles like leptons or neutralinos, the detectors found nothing. Some theorists argue we might have just missed them. Perhaps superpartners are heavier than predicted, or they decay too quickly to spot. Others propose stealth SUSY models where these particles interact so weakly with ordinary matter that they slip through our experiments like ghosts through walls. There's even the radical idea of split supersymmetry, where only some superpartners remain light enough to detect while others hide at scales far beyond our reach. The stakes couldn't be higher. Without SUSY, the Higgs field's instability, the same one that threatens vacuum decay, becomes even more precarious, and dark matter, which makes up 27% of the cosmos, loses its most promising candidate, the neutralino, a hypothetical superpartner that could be lurking everywhere, invisible and untouched. If SUSY isn't real, we're back to square one, forced to explain why the universe's math seems to hint at symmetry while nature stubbornly refuses to comply. But here's the twist. SUSY's greatest strength might be its flexibility. Unlike rigid theories that shatter with a single failed prediction, supersymmetry adapts. Some versions propose extra dimensions where superpartners hide. Others suggest they're hiding in plain sight, masquerading as known particles under certain conditions. It's as if the universe left us a riddle with 1,000 possible answers, each more tantalizing than the last. Whether Sussy is confirmed or not, its legacy is undeniable. It's pushed detectors to their limits, inspired generations of physicists, and revealed just how much we still don't know. The hunt for supersymmetry isn't just about particles. It's a test of whether the universe plays by the elegant rules we've dreamed up, or if it's laughing at us from somewhere beyond the equations. And until we know for sure, those hidden partners will keep haunting the edges of reality, daring us to look deeper. What if the smooth fabric of spacetime isn't fundamental at all, but stitched together from tiny geometric shards like a cosmic mosaic where each tile is a piece of reality itself? That's the bold vision of causal dynamical triangulations, a theory that rebuilds the universe from the ground up using nothing but simple shapes and strict rules of cause and effect. Forget the infinite densities of singularities or the fuzzy quantum foam here. Spacetime emerges from the collective behavior of countless microscopic building blocks, each interacting in a way that keeps the cosmic story logical and coherent. The idea starts with triangles specifically, four-dimensional analogues called simplices. Picture a pyramid but with a triangular base stretched through time. These are the atoms of spacetime in this model, and they snap together like Lego bricks to form the larger structure of the universe. But there's a crucial twist. Unlike other quantum gravity approaches that allow wild, disconnected geometries, causal dynamical triangulations enforce a strict order. Every simplex must connect to its neighbors in a way that preserves causality, no time travel, no loops where effects precede causes. It's as if the universe is assembling itself under the watchful eye of a cosmic editor, ensuring every piece fits seamlessly into a story that makes sense. This rigid structure has a stunning consequence. The Big Bang ceases to be a singularity. Instead, the theory predicts a natural bounce, where the universe reaches a minimum size before expanding again. Imagine squeezing a sponge until it resists further compression, then springs back to its original shape. In this model, spacetime behaves similarly, collapsing to a dense but finite state, then rebounding without ever collapsing into an infinitely small point. The equations even hint at a pre-Big Bang phase, a contraction that set the stage for our expanding cosmos. It's a vision that swaps the terrifying infinity of a singularity for something far more elegant, a universe that folds and unfolds like a cosmic accordion. Supporters highlight the theory's predictive power. Unlike some quantum gravity models that rely on untested extra dimensions or undiscovered particles, causal dynamical triangulations uses only well-established ingredients, geometry, and causality to generate a universe that looks remarkably like ours. Computer simulations of these triangulations show spontaneous emergence of four-dimensional spacetime at large scales, even though the individual building blocks are simpler and lower dimensional. It's as if you stacked a pile of flat triangles together, only to step back and see a sphere, a higher dimensional structure arising from humble parts. Critics, though, question the approach's simplicity. Enforcing strict causality might seem like common sense, but some argue quantum gravity should allow for more exotic possibilities, like microscopic wormholes or timeless states. Others note that the theory struggles to incorporate matter and energy seamlessly. It's great at building empty spacetime, but filling it with stars, galaxies, and quantum fields remains a challenge. And while the math avoids singularities beautifully, there's no direct experimental evidence yet to confirm these geometric building blocks are more than a clever abstraction. Still, the theory's elegance is undeniable. In a realm where most quantum gravity models feel like trying to build a skyscraper with quicksand, causal dynamical triangulations offers solid ground. Each simplex is a tiny vote for order in a chaotic quantum landscape, and together they weave a universe where time flows forward, causes lead to effects, and the Big Bang becomes a transition rather than a barrier. It's a reminder that sometimes the most profound truths aren't found in complexity, but in the quiet harmony of simple shapes playing by the rules. The early universe wasn't the smooth, uniform soup we often imagine. It might have been a seething quantum storm, riddled with microscopic wrinkles that later stretched into the vast cosmic web we see today. This is the wild premise of quantum anisotropy, a theory suggesting that the seeds of galaxies, clusters, and superclusters were planted not by random chance, but by quantum fluctuations frozen into the fabric of spacetime during inflation. Picture a calm lake suddenly hit by a gust of wind. Tiny ripples form, then expand into waves that rearrange the entire surface. Now replace the lake with the newborn cosmos and the wind with quantum uncertainty, and you've got a glimpse of how the universe's largest structures might trace back to its smallest possible scales. The evidence for this lies in the cosmic microwave background, the oldest light we can see. Telescopes like Bicep and Planck have scanned this primordial glow with unprecedented precision, revealing faint temperature variations, hot and cold spots no larger than 1 part in 100,000. These aren't random noise, they're cosmic fossils, imprints of quantum ripples magnified to astronomical scales by inflation's exponential stretching. But here's the twist: some of these fluctuations appear slightly stretched in certain directions, as if spacetime itself had a subtle grain, like wood. This preferred direction, called anisotropy, defies the standard assumption that the early universe was perfectly uniform in all directions. Dive deeper, and the implications get even stranger. If confirmed, quantum anisotropy could mean that the fundamental rules of physics weren't identical everywhere in the infant cosmos. Imagine a room where the strength of gravity changes depending on which way you face, or where light travels faster along one axis than another. In the frenetic quantum environment of inflation, such directional dependence might have left scars on spacetime itself, biases woven so deeply into the universe's expansion that they shaped where galaxies would form billions of years later. It's as if the cosmos had a hidden quantum compass, subtly steering the distribution of matter on scales we're only now beginning to map. Not everyone's convinced. Skeptics argue these anomalies could be artifacts of interstellar dust or instrumental noise. After all, the Planck data's strongest anisotropy signal aligns suspiciously well with our solar system's motion through the CMB. Others propose less exotic explanations, like incomplete modeling of inflation's end. But supporters counter that the patterns persist across multiple datasets, and that certain quantum gravity models naturally predict such directional quirks. Some even speculate that anisotropy might be a relic of the pre-inflationary universe, a quantum fingerprint from a time before time as we know it. Whatever the answer, the hunt for cosmic asymmetry is more than academic. It's a probe into the universe's quantum origins. If anisotropies hold up, they could reveal hidden layers of physics operating at energies far beyond what any particle collider could reach. The night sky, with its glittering galaxies and vast voids, might not just be the aftermath of a chaotic birth. It could be a quantum snapshot, frozen in light, of the moment reality first decided which way was up. Imagine the universe as a cosmic hard drive, where every particle, every force, every ripple in spacetime is just a carefully arranged string of quantum information, except this isn't just a metaphor. Some physicists now suspect reality itself might be a kind of quantum error-correcting code, an unimaginably complex program constantly scanning for glitches and repairing them before they can unravel the fabric of existence. This isn't science fiction, it's a radical solution to one of physics' greatest puzzles. How does information escape a black hole? At the heart of this idea lies the black hole information paradox. When matter falls into a black hole, general relativity says it's crushed into oblivion at the singularity, its information lost forever. But quantum mechanics insists information can't be destroyed. It might scramble, but it never disappears. For decades, these two pillars of physics seemed irreconcilable. Then came the holographic principle, suggesting black holes encode swallowed information on their event horizons like data on a cosmic hard drive. But how does that information stay intact in such a chaotic environment? Enter quantum error correction. Think of spacetime as a vast, self-healing network. Just like your phone's signal compensates for static by redundantly encoding data, the universe might protect its quantum information by distributing it across hidden correlations in the fabric of reality. When a black hole evaporates via Hawking radiation, it's not spewing random noise, it's slowly decrypting the information it swallowed, using error-correcting protocols woven into spacetime itself. The event horizon acts like a cosmic firewall, not to burn things up, but to scramble and preserve data in a way that even the black hole's fury can't corrupt. Support for this idea comes from surprising places. In 2014, physicists discovered that the equations governing quantum error correction in computers perfectly match those describing how spacetime warps under gravity in anti-de Sitter space, a theoretical model of the universe. It's as if Einstein's equations were secretly blueprints for a cosmic repair manual all along. Even more mind-bending, this might explain why entangled particles seem to communicate faster than light. They're not sending signals, they're accessing shared error-correcting data stitched into spacetime's very architecture. Critics argue the analogy is speculative, a mathematical coincidence stretched too far. After all, we've never observed spacetime correcting an error, and the theory works cleanly only in highly abstract universes, not necessarily our own. Yet proponents counter that black hole thermodynamics once seemed equally speculative until Hawking proved they radiate. If spacetime really is a quantum code, it would mean the universe isn't just governed by laws, but actively maintains them, like a cosmic IT department constantly patching reality's operating system. The implications are staggering. If true, every particle interaction, every galaxy collision, even your own thoughts might be underwritten by an invisible layer of quantum redundancy, ensuring coherence against the chaos. The Big Bang wasn't just an explosion, it was the first line of code in a self-repairing cosmic program, one where black holes aren't bugs but features, acting as natural error-correcting nodes in the universe's grand computation. And if that's the case, the real mystery isn't why the cosmos is so orderly, it's who or what wrote the original protocol. What if the smooth, predictable space we navigate every day is just an illusion, a low-resolution approximation of a far stranger, grainier reality? Non-commutative geometry, a bold mathematical framework pioneered by Elaine Connes, suggests that at the tiniest scales, spacetime itself might lose all familiar notions of order, becoming a chaotic realm where coordinates refuse to follow the rules. Imagine trying to pinpoint a location on a map where latitude and longitude no longer commute, where measuring north-south first gives a different result than east-west first. In this quantum terrain, the very concept of here and now blurs, rewriting not just how we see the universe, but how it could have begun. Connes' work reveals a startling possibility. The Big Bang singularity might not have been a point of infinite density, but a phase where spacetime's geometry became so scrambled that traditional physics breaks down entirely. Instead of a violent explosion from nothing, the universe's birth could have been a geometric reorganization, a moment when non-commutative quantum fuzziness crystallized into the structured spacetime we recognize. Picture an ice sheet forming on a turbulent lake. The chaotic ripples of the water don't vanish but become locked into a stable, ordered surface. Similarly, the universe's infancy might have been a bubbling quantum foam where positions and momenta jostled unpredictably until suddenly they froze into the familiar commutative geometry we see today. The implications ripple outward. If spacetime has an irreducible fuzziness at its core, even black holes might not be true singularities, just regions where geometry reverts to its wild, non-commutative roots. The event horizon could act as a boundary not just for light, but for the very rules of localization, a curtain beyond which where and when lose all meaning. This could solve the black hole information paradox by ensuring information never reaches a singular point of destruction. It just enters a state where traditional notions of location no longer apply. But how do we test such an abstract idea? Surprisingly, there are observational clues. Some models predict that non-commutative geometry would subtly alter how high-energy gamma rays travel across the universe. If spacetime has a fundamental graininess, photons of different energies might propagate at very slightly different speeds, an effect that could accumulate over billions of light years. Experiments like the Fermi Gamma Ray Space Telescope have hunted for these delays, though conclusive evidence remains elusive. Another potential signature lurks in the cosmic microwave background. If the early universe's geometry was truly non-commutative, it might have left odd statistical fingerprints in the polarization patterns of this primordial light, deviations from the standard inflationary predictions that future telescopes could uncover. Critics argue that non-commutative geometry strays too far into mathematical abstraction without clear experimental validation. Yet supporters counter that quantum mechanics once faced similar skepticism until its predictions were confirmed in labs worldwide. The theory's elegance is undeniable. It doesn't invent new dimensions or particles, but reimagines the very stage on which reality plays out. And if correct, it hints at a cosmos where the Big Bang wasn't the absolute beginning, but a phase transition in an eternal quantum landscape, one where geometry itself is the deepest, most malleable layer of all. What if the Big Bang wasn't the beginning, but just the universe catching its breath? Quantum bouncing cosmology flips the script on traditional origin stories, proposing that our expanding cosmos wasn't born from a singularity, but rebounded from a previous collapse like a cosmic rubber band snapping back. This isn't just a tweak to the standard model, it's a complete reimagining of cosmic history, where time stretches infinitely in both directions, and the universe cycles through phases of contraction and expansion without ever reaching the crushing infinities of a singularity. Picture a gymnast on a trampoline. As they descend, their motion slows momentarily at the lowest point before surging upward again. In bouncing cosmology, the universe behaves similarly. During contraction, quantum effects become dominant at extremely high densities, generating a repulsive force that counteracts gravity's crush. Instead of collapsing into an infinitely dense point, spacetime reaches a minimum finite size, a Planck scale bounce before reversing course. The math behind this is elegant. Loop quantum gravity and string theory both suggest spacetime has a discrete, granular structure at tiny scales, preventing the infinite densities predicted by classical relativity. It's like discovering the universe has a built-in flaw, stopping the gravitational freefall before it becomes catastrophic. The observational stakes couldn't be higher. Inflationary theory predicts a near-perfectly flat universe with specific patterns in the cosmic microwave background, predictions spectacularly confirmed by missions like Planck. But bounce models leave different fingerprints. Some versions suggest primordial gravitational waves from the bounce would have a distinctive helical polarization, twisting spacetime in ways inflation alone can't explain. Others predict subtle asymmetries in the distribution of galaxies' fossil imprints of the universe's pre-bounce contraction phase, the most tantalizing possibility. A faint echo of the before universe might linger in the CMB's coldest spots, like shadows cast by a cosmos that once was. Critics highlight the challenges. Without a singular beginning, entropy becomes a puzzle. Why doesn't each cycle grow messier, with disorder accumulating over infinite time? Some theorists propose that quantum reset mechanisms purge entropy at each bounce, like a cosmic etch-a-sketch being shaken clean. Others argue that entropy doesn't need resetting, it's simply diluted during expansion, leaving each new cycle fresh. The debate rages, but the mere possibility reshapes our cosmic narrative. No longer a one-off event, the Big Bang becomes a turning point in an eternal rhythm, with black holes in one cycle possibly seeding galaxy formation in the next. The most profound implication: time loses its arrow. In a bouncing universe, there's no definitive before or after, just an endless oscillation where each phase blends seamlessly into its opposite. The cosmos becomes a living entity, breathing in and out across eons, with every collapse not an end but a rebirth. And if that's true, our universe's story isn't a solo performance, it's part of an infinite encore, playing to an audience of atoms that will one day gather, disperse, and gather again in a dance without end. Dark matter has been the universe's most stubborn enigma for nearly a century, an invisible something whose gravitational grip holds galaxies together, yet refuses to interact with light or ordinary matter in any way we can directly detect. But what if its elusiveness isn't just an observational challenge, but a clue to its true nature? Some theorists now suspect dark matter might not be a particle at all in the traditional sense, but a shadowy quantum field humming through the cosmos, its presence felt only through the subtle warping of spacetime itself. This idea springs from the quantum world's strangest corners. Just as the Higgs field gives particles mass by dragging on them like cosmic molasses, an undiscovered quantum field, or family of fields, could be shaping the universe in ways we've only begun to imagine. Think of space not as empty but as a vast ocean with invisible currents. Dark matter's pull could be the gravitational wake of these hidden flows, their ripples sculpting galaxies without ever bumping into atoms. One leading candidate for such a field is the action, a hypothetical particle so lightweight and weakly interacting that it behaves more like a wave than a discrete speck of matter. If actions exist, they'd form a universe spanning quantum condensate, a superfluid so delicate it could pass through planets like a breeze through a screen door. The hunt for these quantum phantoms is already underway. Experiments like ADAMS use ultra-sensitive microwave cavities to coax actions into revealing themselves, tuning their detectors like cosmic radios, hoping to catch the faint click of a dark matter particle converting into a photon. Others search for subtle distortions in neutron stars' magnetic fields, where action-like particles might leave ghostly fingerprints. Even Earth's own magnetic field could be a natural action detector. Some proposals suggest satellites might spot anomalies caused by dark matter's quantum whispers. Yet not everyone agrees this is the right path. Modified gravity theories like MUND argue dark matter is a mirage, a sign that Einstein's relativity breaks down on galactic scales. They point to peculiar galaxy rotation curves that seem to follow predictable patterns, as if some unseen hand tweaked gravity's rules at low accelerations. But quantum dark matter proponents counter that no modified gravity model yet explains all the evidence, from galaxy cluster collisions to the cosmic microwave background's precise fluctuations. The bullet cluster, where visible matter and gravitational lensing clearly separate, remains a thorn in MUND's side, a cosmic crime scene where the invisible suspect seems undeniably real. The debate cuts to the heart of modern physics. If dark matter arises from quantum fields, it would mean the universe is doubly woven from invisible threads, not just the Higgs but a darker tapestry underpinning reality. If it's modified gravity, our understanding of spacetime itself needs rewriting. Or perhaps the truth lies in between. Emergent gravity theories now explore how spacetime's structure might naturally give rise to effects we attribute to dark matter, like a cosmic illusion born from quantum entanglement's deep geometry. One thing's certain: solving this riddle won't just reveal what dark matter is, it'll redefine our place in the quantum cosmos. Whether it's actions, hidden fields, or gravity's redesign, the answer waits in the quietest corners of the universe, where reality's faintest signals whisper their secrets to those patient enough to listen. Gravity, the force that sculpts galaxies and pins us to the ground, might not be a fundamental force at all. According to physicist Eric Verland, what we perceive as gravity could be nothing more than a cosmic mirage, an emergent side effect of something far deeper, the universe's relentless march toward disorder. This radical idea, known as entropic gravity, suggests that the pull we feel isn't the result of mass-warping spacetime, as Einstein taught us, but the universe's way of maximizing entropy, the natural tendency of systems to descend into chaos. Imagine a crowd of people shuffling to distribute themselves evenly across a room, not because they're drawn by some invisible force, but simply because it's the most statistically likely arrangement. In Verland's vision, gravity works the same way. Objects don't attract each other. They're nudged together by the universe's drive to spread energy as evenly as possible. At the heart of this theory lies a stunning reversal of perspective. Instead of gravity causing entropy, entropy produces gravity. When a star or planet sits in space, it creates a kind of cosmic imbalance, a region where information and thus entropy is locally higher. The universe, striving to restore equilibrium, effectively pushes objects toward each other to redistribute this informational load. It's as if spacetime itself were a stretched rubber sheet, not because mass bends it, but because the quantum bits encoding reality rearrange themselves to balance the books. This isn't just philosophical sleight of hand. Verland's equations reproduce Newton's law of gravitation and even predict deviations that could explain dark matter's effects without invoking any invisible particles. Now apply this to the Big Bang. If gravity isn't fundamental, the singularity, that infinitely dense point where relativity breaks down, might never have existed. Instead, the universe's birth could have been a thermodynamic phase transition, a moment when the cosmic information budget tipped into a new state. Picture a frozen lake melting in spring. The ice doesn't vanish into a singularity. It transforms smoothly into water as thermal energy reshapes its structure. Similarly, the early universe might have thawed from a high entropy state into the expanding cosmos we see today, with gravity emerging as a byproduct of this informational reshuffling. No infinite densities, no cosmic egg, just the universe finding a new way to balance its ledger. Critics are quick to point out the gaps. Entropic gravity struggles to explain precise phenomena like gravitational lensing or the orbits of binary pulsars without ad hoc tweaks. And without a clear quantum mechanical foundation, some argue it's more metaphor than mechanism. Yet supporters highlight its explanatory power. By treating gravity as an entropic force, Verland's framework naturally accounts for dark energy's accelerating expansion, a cosmic drive toward maximum disorder. It also dovetails with the holographic principle, where the universe's information is stored on its boundary, not in its volume, the most tantalizing implication. If gravity is emergent, the universe's origins might be too. Rather than a singular explosion, the Big Bang could mark the moment when information, the true currency of reality, first crystallized into the rules we call physics. In this view, spacetime isn't the stage, it's part of the play, an act in a grand thermodynamic drama where entropy writes the script. And if that's true, the cosmos isn't just expanding, it's learning, unfolding new chapters in a story where gravity is just the ink on the page. What if the Big Bang wasn't an explosion but a tunnel? Quantum wormhole genesis turns the cosmic origin story inside out, proposing our universe didn't burst into existence from nothingness, but emerged from the throat of a traversable wormhole, a cosmic shortcut stitching together realities. This isn't just speculative fantasy. It's grounded in the same equations Einstein and Rosen used to theorize bridges between distant points in spacetime. But here's the twist. Modern quantum physics suggests these bridges might not just connect regions of our universe, they could birth entirely new ones. Picture a black hole collapsing in some parent universe, its singularity stretching into a funnel that punches through to another realm. Instead of ending in oblivion, the collapsing matter surges through this wormhole's throat, rebounding as an expanding fireball on the other side. a new cosmos with its own laws, its own spacetime, its own destiny. Recent breakthroughs in quantum teleportation add eerie plausibility to this idea. Scientists have already teleported quantum states across labs using entanglement, a phenomenon Einstein called spooky action at a distance. Scale this up to cosmic proportions, and you could imagine entire universes quantum tunneling into existence, their physical constants determined by the wormhole's geometry, like a cosmic printer setting its parameters before hitting start. The math reveals even wilder possibilities. Wormholes threaded with exotic matter, a theoretical substance with negative energy, could remain stable enough to transport not just particles but spacetime itself. In this scenario, the Big Bang singularity isn't a dead end but a gateway. The universe's seemingly inexplicable uniformity, its near-perfect balance of matter and energy, might simply reflect conditions in the wormhole's throat, smoothed out during transition like dough stretched through a rolling pin. Even dark energy's mysterious push could trace back to residual tension in the wormhole's structure, a cosmic echo of the tunnel that birthed us. Skeptics highlight the hurdles. Traversable wormholes require exotic matter we've never observed, and quantum gravity's unfinished framework leaves key questions unanswered, yet supporters point to tantalizing clues. The AR equals EPR conjecture, linking wormholes to quantum entanglement, suggests spacetime itself might be woven from hidden wormhole-like connections. And if black holes preserve information on their event horizons as holograms, could a wormhole's exit point holographically project an entire universe? The most mind-bending implication: if wormholes can spawn universes, ours might be part of an infinite family tree, each cosmos budding from another's spacetime defects. The night sky wouldn't just be a window to the past, it might be a reflection of our cosmic ancestry, a holographic imprint of the tunnel that brought us here. And if that's true, the ultimate question isn't how our universe began, but what lies on the other side of the door. Zoom into the fabric of spacetime far enough, and you might find a universe within the universe, an endlessly repeating pattern where every layer, no matter how small, echoes the whole. This is the fractal quantum universe hypothesis, a mind-bending vision where reality isn't just built from particles or strings, but from self-similar structures that mirror the cosmos at every scale. Imagine a cosmic Russian nesting doll where galaxies resemble atoms and quantum fluctuations mirror the swirling arms of nebulae. It's an idea inspired by the work of mathematician Benoit Mandelbrot, who revealed how infinite complexity could arise from simple recursive rules, like the jagged coastline of a continent repeating its shape in every pebble and grain of sand. At the heart of this theory lies a radical reimagining of spacetime's architecture. Instead of smooth geometry or discrete quanta, the universe might be a fractal, a mathematical tapestry where patterns repeat whether you're looking at the span of a supercluster or the spin of an electron. Some models suggest quantum foam, that seething Planck-scale chaos, isn't random at all, but organized into fractal networks of wormholes or entangled connections. Picture the branching veins of a leaf or the lightning-like forks of a Lichtenberg figure. Now imagine that same structure governing the quantum vacuum itself, with tiny fluctuations echoing the large-scale distribution of galaxies we see today. The observational challenges are immense. Fractal patterns thrive on scale invariance, the idea that a system looks the same zoomed in or out. But our universe clearly changes behavior across scales. Gravity dominates galaxies while quantum rules govern atoms. To bridge this gap, theorists propose relative fractality, where only certain properties like the clustering of matter or the distribution of energy repeat across scales. Others tweak the math, suggesting fractal geometry might emerge only in extreme conditions, like near black hole singularities or during the Big Bang's first moments. Yet there are tantalizing clues. The large-scale structure of the cosmos, with its galaxy clusters and cosmic voids, bears an uncanny resemblance to neural networks or fungal mycelium, natural fractals that balance order and chaos. Even the cosmic microwave background's temperature fluctuations, though statistically Gaussian, contain anomalous cold spots and asymmetries that some argue could be fingerprints of a deeper fractal order. Critics argue these patterns are coincidental, the result of universal physical processes rather than true self-similarity. After all, gravity naturally clumps matter into hierarchies without invoking fractals. But supporters counter that quantum entanglement, with its non-local connections, might provide the mechanism for scale jumping patterns, weaving the universe into a unified fractal whole. If the fractal quantum universe is real, it would mean the cosmos isn't just governed by symmetry, it is symmetry, a living equation where every part reflects the whole. The Big Bang wasn't a beginning, but a transformation, one twist in an infinite spiral of existence, forever repeating, forever new. Neutrinos, the universe's most elusive particles, might have played a far bigger role in shaping reality than we ever imagined. These ghostly particles, so light they were once thought to be massless, stream through you by the trillions every second, barely interacting with anything. Yet their minuscule masses could have been the secret architects of cosmic inflation, the explosive expansion that set the stage for everything we see. Picture this: in the first fractions of a second after the Big Bang, while the cosmos was a seething plasma, neutrinos weren't just passive spectators, they were quantum puppeteers tugging at the fabric of spacetime itself. The key lies in a phenomenon called neutrino oscillation. Experiments like Super Kamiokande and Ice Cube have shown that neutrinos can morph between three flavors: electron, muon, and tau as they travel. This chameleon-like behavior proves they have mass, albeit infinitesimal. But in the early universe's extreme densities, even these tiny masses could have tipped the scales. Some theories suggest that as neutrinos oscillated, they released energy in a way that amplified inflation, stretching spacetime faster than light and smoothing the universe into the eerily uniform cosmos we observe today. It's as if a swarm of cosmic butterflies flapped their wings just right, creating a hurricane of expansion that shaped galaxies billions of years later. This isn't just speculation, it ties into leptogenesis, a leading explanation for why the universe is made of matter rather than antimatter. Neutrinos, with their knack for flipping identities, could have triggered a slight asymmetry in the early plasma, favoring the creation of matter particles over their antimatter twins. Imagine a cosmic seesaw. As heavy neutrinos decayed in the hot young universe, they might have spat out just enough extra electrons and quarks to tip the balance. Over billions of years, that tiny excess became all the stars, planets, and even us. The evidence is mounting. Cosmic microwave background data shows patterns consistent with neutrino-driven inflation, and particle colliders are narrowing down neutrino mass ranges. Future experiments like Dune aim to catch these particles mid-oscillation, potentially revealing how they sculpted spacetime. Critics argue neutrinos are too light to wield such influence, but supporters counter that in the seething energy of the early cosmos, even featherweight particles could have outsized effects when acting on mass. If this theory holds, the universe wasn't just shaped by gravity or quantum fields. It was fine-tuned by particles so elusive we barely knew they existed. The next time you feel sunlight on your skin, remember, those photons began their journey in a star, but the stage for that star was set by neutrinos dancing in the dark. What if consciousness isn't just a byproduct of the universe, but the very force that sculpts it into being? Quantum consciousness cosmology proposes a radical inversion of reality, that the act of observation doesn't merely measure quantum systems, but creates them, collapsing waves of possibility into concrete existence. This idea, often dismissed as fringe by mainstream physicists, draws eerie parallels with ancient Eastern philosophies, while challenging the bedrock assumption that reality exists independent of the mind. At the quantum level, particles exist in superposition, a haze of probabilities until measured. The classic double-slit experiment reveals this starkly. Electrons behave as waves when unobserved, producing interference patterns, but snap into definite particle states the moment a detector intervenes. The Copenhagen interpretation treats this as a mathematical quirk, but quantum consciousness takes it further. What if the detector's observation requires something deeper, not just a machine, but a mind to register the result? In this view, consciousness isn't passive, it's the cosmic sculptor chiseling reality from quantum potential like a potter shaping clay. The theory's roots intertwine with Eastern mysticism. Hindu Vedanta describes Brahman as the ultimate reality, where observer and observed are one, a concept mirroring quantum entanglement's inseparability. Buddhist teachings assert that phenomena lack inherent existence until perceived, echoing the quantum wave function's collapse. Even Taoism's yin-yang, with its dance of complementary opposites, finds kinship in particle-wave duality. These parallels aren't mere coincidence, argue proponents like physicist Amit Goswami. They're glimpses of a deeper truth Western science is only beginning to grasp. Yet critics pounce on the gaps. If consciousness collapses wave functions, whose consciousness, a human's, a cat's, a bacterium's, the theory struggles to define a threshold for observer status. Worse, it seems to revive the discredited consciousness causes collapse interpretation of quantum mechanics. An idea largely abandoned after decoherence theory showed environmental interactions can collapse wave functions without minds. The universe existed for billions of years before life emerged. Did reality remain in limbo until the first conscious organism blinked it into focus? Supporters counter with panpsychism, the view that consciousness is fundamental, not emergent. In this framework, even elementary particles possess rudimentary awareness, and complex observers like humans simply amplify this inherent property. Recent work in integrated information theory lends tentative support, suggesting consciousness arises from specific configurations of information processing, a property not exclusive to brains. If true, the cosmos might be a vast network of proto-conscious events, each observation from a photon hitting a leaf to a scientist recording data contributing to reality's unfolding. The debate crescendos when applied to cosmology. Could the universe's fine-tuning, its perfect balance of constants for life, reflect a kind of self-aware bootstrap where future observers retroactively shape their origins? It's a dizzying loop, but one that resonates with Wheeler's participatory universe. And if consciousness is indeed foundational, the Big Bang wasn't just a physical event, it was the first act of cosmic attention, a primal observation that ignited spacetime itself. Whether quantum consciousness cosmology ever earns scientific acceptance, it forces a profound question. Are we passive witnesses to reality or co-creators of it? The answer might lie not in equations alone, but in the elusive intersection of quantum physics, philosophy, and the ancient intuition that to observe the universe is in some deep way to bring it into being. Of all the strange ideas in modern physics, none is more counterintuitive than this. Everything we see, every star, every galaxy, even the device you're watching this on might ultimately cancel out to nothing. This is the null universe hypothesis, a radical proposal that the cosmos is the ultimate free lunch, balancing its books so perfectly that the total energy of existence sums precisely to zero. At first glance, it sounds impossible. How could trillions of galaxies full of matter and energy amount to nothing? But the answer lies in a cosmic accounting trick so elegant, it rewrites our understanding of creation itself. The magic happens when you consider gravity's ledger. While matter and energy contribute positive values to the universe's balance sheet, gravity, the curvature of spacetime itself, carries negative energy. Picture a child building a sandcastle. The mound of sand represents positive energy, but the hole they dug to gather that sand is an equal negative. On cosmic scales, Einstein's equations reveal something astonishing. The gravitational potential energy of the universe exactly cancels out the positive energy of its matter and radiation. It's as if the cosmos is a meticulously balanced equation, with every particle of light or drop of dark matter matched by a corresponding debt in the fabric of spacetime. Quantum field theory adds another layer to this cosmic symmetry. In the quantum vacuum, particles constantly flicker in and out of existence, their fleeting lives governed by the principle that energy can be borrowed so long as it's repaid quickly. The null universe hypothesis takes this idea to its ultimate conclusion. If the vacuum can briefly spawn particles from nothing, why not an entire universe? In this view, the Big Bang wasn't an injection of energy from some external source, but a quantum fluctuation so vast it balanced creation and cancellation on a cosmic scale. Matter and gravity locked in an eternal dance, each step perfectly countering the other. Critics argue this can't explain why the universe is structured the way it is, why stars form, why life exists if everything ultimately nets to zero. But supporters counter that imbalance is the engine of complexity. Think of a battery. Its positive and negative terminals cancel out overall, yet the potential difference between them powers everything from smartphones to supernova. Similarly, the tension between the universe's positive and negative energies might be what fuels galaxies, drives expansion, and even makes life possible. The zero isn't a void, it's a dynamic equilibrium humming with creative potential. The most mind-bending implication: if the null hypothesis holds, then existence isn't just allowed to arise from nothing, it's inevitable. In an infinite quantum sea, fluctuations balancing to zero would be the rule, not the exception. Universes might bubble up constantly, most collapsing instantly, while rare ones like ours strike the delicate balance needed to persist. Suddenly, the question isn't, why is there something rather than nothing, but why wouldn't there be? A cosmic shrug written into the fabric of reality itself. From the infinite froth of bubble universes to the cosmic hologram projected from a distant boundary, from self-aware Boltzmann brains hallucinating reality to the universe balancing its books at zero, we've journeyed through a labyrinth of quantum origin theories so wild, they blur the line between science and imagination. Each one challenges our most basic assumptions about existence, proving that the deeper we peer into the cosmos' birth, the stranger the story becomes. These aren't just thought experiments, they're the cutting edge of human curiosity, where physicists wrestle with equations that hint at realities beyond our senses, where black holes might be cosmic wombs and spacetime itself could be stitched from quantum threads we've yet to untangle. What's astonishing isn't just the diversity of these ideas, it's how they refuse to settle. For every theory that claims the Big Bang was a singularity, another argues it was a bounce. For every model where observation creates reality, another insists reality was always there, just hiding in the math. This isn't chaos, it's the sound of science straining at its limits, daring to ask questions that once belonged only to philosophers and dreamers. And that's the beauty of it. The universe's origins aren't a puzzle with one missing piece, but a kaleidoscope where every twist reveals new patterns, new possibilities. So where does that leave us? Right where science thrives most, in the unknown. The very fact that these theories exist, each with its own tantalizing shred of evidence and elegant logic, means we're closer than ever to something revolutionary. Maybe the next breakthrough will come from a lab, a telescope, or a lone physicist scribbling equations at midnight. Or maybe it's already hidden in plain sight, waiting for us to ask the right question. One thing's certain, the universe's origin story is still being written, and we all get to be part of it. Stay curious, stay bold, and keep looking up. The next quantum leap in understanding could be just around the corner.